Okay. So here we're gonna have left pointer, left and right pointer, and then while I think we can skip that actually, but calculate the middle. We have a left and right pointer, and while the left and right pointer are while the left pointer is less than the right pointer, we're going to calculate the middle index. Check if we have found the target, and then based on the middle's value relative to the target, close the search window by the smaller half or the lower half. So here we do in left, right equals left plus right minus left divided by 2. This is to prevent integer overflow. And if the middle index equals target, then we return what? The index? Yeah. And then if it doesn't, then if it's less than target, the left will equal the middle plus 1, otherwise the right will equal the middle minus 1. And then here we have to return -1 as a failsafe. And this will occur in O of n log, or O of log n. Yeah. This needs to be equal to. There we go. Okay. This is based off the same principle. We're going to have a left and right pointer. Based off of this grid. So what we're going to do is we're going to take this grid and flatten it out. So we're going to say 1, 2, 3, 4, 5, 6, 7, 10, 11, or 1, 3, 5, 7, 10, 11, 16, 20, 23, 30, 34, and 60, and act as if it's in one long array rather than a two-dimensional array like so. So we'll have the left and right pointer, and we'll calculate that using the matrix values. The matrix length values. And then we're going to do the same thing. We will calculate the middle index, and then check if we have found the target, and then if we haven't found the target, we will partition the matrix, or partition the search values. So here we'll have left, and then this will be the area of the matrix minus 1. And then here we'll have while left is less than or equal to right. We'll calculate the middle, and we'll do left plus right minus left divided by 2 to avoid integer overflow. And then if we also need to calculate the x and y coordinates, or sorry, the row and column, the coordinates of the value. So here row equals, the row will equal the middle value divided by the matrix's longest length, and then the column will be the middle value remainder of the matrix's longest length. So if the matrix row and column equals target, we return true. And then if that value is less than the target, then we're going to do left equals middle plus 1. And the same thing, right, equals middle minus 1. And then return false if otherwise. Length. There we go. And this will occur in O of log n. Actually, it would be O of log n times m, where n is the n is the length and m is the height. But if you take the input size, then it's n. Space complexity is n, or constant. Oh, this one's complicated. So how we're going to do this is we're going to calculate the minimum and maximum eating speed, and then what? While we and then we're going to converge on the minimum eating speed for within h hours. So then after that, how we do that is we're going to calculate the middle or the average eating speed. And then we're going to calculate the time it takes to eat at the average, or calculate the time, the eating time with the average speed. And then and then based off of that calculation, we're going to refine our eating speeds, our possible eating speeds. And then we're going to wait for the left and right pointers the minimum and maximum pointers to converge. So here, min will always equal 1, because we can always eat, or the minimum amount of bananas we can eat at a given hour is 1. And then max will equal 1 as well, but we will need to calculate max based off of the bananas in each pile. So max will equal the max of each pile of bananas, and then while the min is less than or equal to the max, we will make all these calculations. So if we want to calculate the average, we're going to do what is it? It's min plus max minus min divided by 2. And then we're going to calculate the eating speed. So for each pile of bananas, we're going to take it's right here. I'm going to take hours and add the bananas divided by the average speed and get the ceiling of that. We want to round up every time. and then we're going to typecast this back into an integer. And then based off of how many hours that takes, we're going to refine the eating speed. So if the amount of hours it took at the average speed is less than or equal to the amount of hours, then we're going to make the maximum equal the average. Otherwise, we're going to make the minimum equal the average plus 1. And then we'll return the minimum. Yeah, we're going to return the minimum. So we do this because we will have rounding errors with the ceiling value here. And just because the amount of hours for our average eating speed is equal to the amount of hours that we're looking for, it doesn't mean that the average amount of bananas that are eaten during this calculation is the lowest, is the minimum number that we can eat all the bananas within those hours, because 1 minus the average could still yield the same number because of how we're handling these, because we're rounding up in the hours, basically. And I think this will... Nope. Okay, so we might have to do this. There we go. Beautiful. Okay, find minimum and rotate sort array. So we're going to have a left and right pointer. And then we're going to find the minimum. We will calculate the middle index. And based off of that middle index, and whether the left pointer and the right pointer is greater than or equal to, or sorry, greater than or less than it, we will understand how to reduce the search array from there. What I mean by that is, if we have the middle index here, we are effective when we have the, or if we're looking for the middle index, we're looking for the point of rotation here. So at the point of rotation, it'll always be the maximum and the minimum. So this isn't rotated, so the point of rotation is at the minimum, sorry. And then this is rotated here, and at the point of rotation, we have the minimum. So we're always looking for the point of rotation. So we are looking for the incorrectly sorted portion of the array. Search for incorrectly sorted portion of array, and then minimize search array size. Cool. So here we'll have int left equals 0, int right equals num style length minus 1, and then while the left is less than or equal to the right, calculate the middle index, so that will be left plus right minus left divided by 2. Search for the incorrectly sorted portion of the array. So if the number at the middle, or sorry, if the number at the left is less than the number at the middle, then the left side is sorted, which means it doesn't have the minimum. So left will equal middle plus, oh, middle, yeah. Because, actually, no, left will not equal middle. It'll be middle plus 1. And then, if this isn't the case, then the right side is sorted, and the right will equal only the middle. This is because if, let's say, num's middle is less than num's right, middle can technically, there's a possibility that middle is the number that we're looking for because it's less than. So we want to make sure that we're not including that. And then we will return. This actually should be less than, I think. We're going to return the right number, because this will slowly just converge, I believe. Maybe not. This will be infinite, yeah. What am I doing wrong? Maybe I'm thinking about this wrong. I think potentially we have to look for if nums dot left is greater than nums middle, then left equals middle, and then right equals middle minus 1. Something like that. And then instead of doing this, we search for left. This might be the case. Okay, never mind. Oh, wait. No, I'm right. I think we're just returning the index, right? No, we're not. It's definitely, okay, this is definitely wrong. So what am I doing wrong? What am I doing wrong? Oh my gosh, wait. Did I do that last time? What am I doing around here? Oh, I know what's wrong. Yes. Okay. So what I was doing wrong before was I was default. You want to prioritize cutting off. You want to prioritize cutting off the right side first, because when in doubt, in this situation, the right side will always be greater than the left side, right? So you want to prune the right side first, just in case. I actually never got that until I just thought about it. That occurred in O of n log, or that occurred in O of log n, and then space complexity was O of 1. Okay, so for the time map, let's see, we are going to create a hash map field to store all the values, and so we're going to create a hash map to store for storing key value pairs. For storing keys and values, yeah. And then, yeah, that's about it. We're going to initialize. We're going to declare here. Declare. Initialize hash map. And then in the constructor. So we declare the hash map as an instance field, and we will initialize the hash map in the constructor. To set a value, we will, I believe you can overwrite keys. So it's like foo bar 1, foo 1. Yeah, so the keys will be strings, and the values will be a list of strings like this. Because we want to be able to store multiple values under the same key based off of their timestamps. Because we're getting timestamps right here. So we want to get the closest timestamp based off of the key. So when we set, we are going to check if the key currently exists. And if it does, then if the key currently exists, oh wait, actually does not currently exist. Currently exist. If it does, then we are going to create a new list, or we're going to put a new list in the hash map based off the key. And then if it does, then we are going to add the value add the value into the list. And then getting, we're going to use binary search to get the value based off of the timestamp that's passed. So here we can do public map string list string map, and then this dot map equals new hash map. And then here, if this dot map dot contains key, if it doesn't, this dot map dot put key new array list, and then this dot map dot get key dot add new pair value timestamp. Okay, and then we are going to create a pair class. So I'm going to create that here, and then we're going to store the values and the timestamps as instance fields. So public string value, public int timestamp, and then in the constructor we will take a value and a timestamp and then assign it to the instance field. Okay. Yeah, that sounds good. So something important about this problem that I didn't realize at first is that all the timestamps are added in strictly increasing order. Like, I thought they were added in random order, but it doesn't really specify. Like, this is pretty ambiguous in terms of, like, I guess, like, yeah, I don't know. I feel like this is still pretty ambiguous. It should say all keys or all, I guess this is not ambiguous. All the timestamps of set are strictly increasing, I guess. I don't know. You have to really look for it, though. So here we're going to run binary search. Actually, we need to check if the key exists. So if this dot map dot contains key, if it doesn't, return a blank. And then here we'll go this dot map dot get key and then timestamp. So we're getting the list and doing that. So we will make a new. We also need to return this. We'll make a new method called binary search, and it will take in a list of strings and a timestamp. Actually, this does not need to be string. This should be pair. Yeah. So then we just do binary search. So we'll have a left and right pointer. Int left equals 0 and int right equals list.size minus 1. And then we will iterate based off of those relative values. And then this should be equal to. So the middle will equal the left plus the right minus the left divided by 2 to avoid integer overflow. And then if list the current middle value equal, or the current middle value's timestamp equals the timestamp that we passed in, we're going to return the middle value's value. Otherwise, if it's less than, if the timestamp is less than the one that we passed in, then left has to equal middle plus 1, and then otherwise right has to equal middle minus 1. And then we can return a blank if we, oh wait, no, that's wrong. So if we don't find it at all, we want to return the entry that was before the timestamp that we were looking for. So if we've converged at this point, so if the right value is greater than or equal to 0, then we will take the right value and return its value. Otherwise, we return nothing. There we go. Beautiful. So time map, the data structure overall will take O of n space. Set will take, let me undo this. So set will take O of 1 time, and then get will take log n time because of the binary search. So yeah. And then I think, yeah, we have like 4 seconds until the daily challenge pops up. It should be live. And it is. Oh my gosh, this is a hard question. Jeez. Okay, find building where Alice and Bob can meet. You're given a 0 indexed array with heights positive, where heights represents the height of the I building. If a person is in building I, they can move to any other building if and only it's ahead of it and it's lower than it. You're also given another array queries. On the ith query, Alice is in building A while Bob is in building B. Okay, so this is Alice's position, Bob's position. Return an array where each index is the index of the leftmost building where Alice and Bob can meet on the ith query. Jeez, bro. If Alice and Bob cannot move to a common building or query, set it to -1. Okay. So 6, 4. Okay. Alice and Bob are at 0 and 1. Leftmost building. So the closest building to the beginning. 0 and 1. So they can meet at 8. Height 0 is less than height 2. Yeah. Okay. Since height's so 0, 3. So Alice is here, Bob's at 3. They can just meet at 3. Right? Oh. Height 0 is less than 5. 0, 1, 2, 3, 4, 5. Okay. And height's 3. Oh, this one. Okay. Yeah. Okay. This actually is not too complicated. So there's no possible for this one. 2, 4. 2, 4. Yeah. Interesting. This doesn't seem impossible, which is good. Okay, so we're going to make an output array. That's going to equal queries.length, I think. Yeah. Okay. And then we need to iterate through each query. And Alice equals, and A equals query 0, and B equals query 1. So we have Alice's and Bob's position. Oh, okay. So we can kind of do a 2-pointer or sliding window kind of. Okay. So while neither of them have exhausted all the heights, we also need to keep track of heights. So height A equals heights A, and height B equals heights B. Okay. Okay. Actually, this will be a lot easier. So it's like I'm definitely overcomplicating this. This is not fun. Okay. We can't do the advanced for loop because we need the current index, and it's just cleaner to do it this way. So then output I will equal, this needs to be J. output I equals. Yeah, it's 0 indexed. Okay. And then break. This is slow. It's not fast. Okay. Yeah. I might run into some time issues. Yeah. Oh, what? I don't know, what did I do wrong? Like, what is... It's the 943rd test case, bro. Okay. Let's see. Can I use... Yeah, use test case. Okay. So what's wrong with this? The third one. 0, 2. 0, 2. I said 2? Why are you saying 2? This should be 3. So math.max AB, because math.max AB should be 2. 1, 2. So it says, it looks at 2. It says 1, 1. Height A is 1. And height B is 1. Does it have to be greater than it? Oh, it does. So, get rid of these. -1. So if we do this, I'm curious to see what portion is wrong. -1. 2, 2. So 8 and 8. Eight, 8. Oh, okay. So it's here. Let's see. 0, 7. 0, 1, 2, 3, 4, 5, 6, 7. think it just equals A. Yeah. And then I can do this. I can do break here, or continue here. Let's see, this should work. Oh wait, sorry. This should work. Never mind. Wait. One, 2, 3, 4, 5, 6, 7, 8. Okay, that makes sense. 7. I see why. This is interesting. So if I do this, this will cover most test cases, but this one. Because we know they don't equal each other. Why isn't this 2? It should be 2. Oh, because it's not greater than it. If they're the same query, that covers that. So if they equal each other, it's looking like this may be the case. Would there be anything wrong with doing this? Oh yeah, I think we'll run into issues if we do this. Yeah. But these are then solved. That's interesting. Wait. Let's look at this one. the fifth query. 1, 2, 3, 0. No, 1, 2, 3, 4, 5. 0, 4, 0, 0, 1, 2, or 0, 1, 2, 3, 4. Yeah, I think this only occurs when you have. So maybe I can do 2 independent loops. Now what? 1, 2, 3, 4, 5, 6, 7, 8, 9, 3, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9, 1, 2. 1, 2. These are screwing me up a lot, but I don't know how to separate them. Because you want it to be equal to. Wait, what's wrong with doing the equal to again? So if we get rid of this and get rid of this, what happens? Maybe we go backwards. So like, no. That's not gonna work. This is faster. We're just doing the opposite. We're inverting it. Like, I don't. Yeah, let me try it. Well, I'll try it, but I don't think it's gonna change anything. I don't think this is gonna change anything. It's the same thing. Yeah. Okay. I think I'm going to look this up. I am stuck. So close though, very close. I wonder what the trick is. I don't like this. Yeah, let's do none of this DFS stuff. What are people saying? Oh, people haven't said anything. Oh my gosh. This is talking about relative to queries, though. Okay, apparently BFS is faster. I had a feeling it was going to be a graph problem, but... this is the definition. This is the method definition. Oh, yeah. Stack. Oh my gosh. Oh my gosh. Why? Why would you? Who does this, bruh? Really? What is the point of that? Why would it ever equal -1? Oh my gosh. Why is it using I and J? Use A and B. My goodness. This is interesting. Look at the setup for this. Terrible. I'm just doing this so it'll refactor to the actual, like, mnemonically named variables. What the heck is this IJBS? Oh my gosh, no. I give up on that. Alright, let's see. stack. No, this should be I. This should be A, B, A, B, B, I, B, A, B, I, B, A, Of course. Of course. I don't know why I trust GPT anymore. Oh my gosh. Please scroll. Jeez. You can store a monotonic stack in an array list? Oh, heck no. Okay. You know what? I'm late for something. So I am going. That was frustrating.